Hello and welcome to this section 6.4 lecture. Today we're going to be talking about fitting a line to data. And so most of the time when we're doing this, we're looking for, we're looking at a set of data, some statistical sort of relationship between two quantities. And that's kind of the key to building a scatter plot. So we're not so much talking about, a pretty common starting point in statistics is let's find the mean, median, and mode of a set of data. Whatever problem would work for that and think about what that would look like, they would just give you a set of numbers and they want you to figure the things out from there. And that's not really what we're looking for here because that would be like one variable data. There's only one thing that's being changed through a problem like that. In this type of scenario, we have what we call bivariate data. And that means that there's two variables happening. We're relating two different pieces of information. So whereas in the mean, median, and mode talk, you could come up with you would have test scores and you would say, what's the mean of these test scores? What's the average of these test scores? That's okay. That's not going to work for scatter plots, though. Okay? A scatter plot is a representation of what we call bivariate. I should say representation of bivariate data. So in order to use something like test scores, we would have to be able to compare, say, here's the scores that a group of students got on a test after studying for different amounts of time, right? So you're comparing the time that they studied to their test score. All right, and then correlation is going to be the overall trend of the data. And as you can see below, we have three types of correlation. We have the first one being a positive correlation. So as one of the variables gets bigger, the other one also gets bigger. So we have something that resembles a positive slope. We have negative correlation, so maybe, as x gets bigger, y gets smaller. And for that, we see that we do have somewhat of a negative slope. And then we have what we consider to be no correlation, where I took this from considers this to be relatively no correlation because just in the picture that you have, there doesn't seem to be any overall trend to the data. Now, of course, you could always look at this and say, well, what would happen if I zoomed way out? If I made this graph a lot bigger and I looked at this from a wider point of view, I may end up seeing that I would have some sort of a correlation just on a grander scale. But And if this was the case, I would say there was a positive correlation. But as it's presented to us, we don't really see any trend in the data. It seems, for lack of a better word, scattered. Okay, and that's, again, just with what we're given here. So based on this information, it is what we're going to mainly consider as just no correlation. I tend to drop the relatively no correlation. Okay, so we can classify sets of data as having different levels of correlation. And whether you look, I guess it depends on where you look, there is typically a strong and a weak correlation. And that's just kind of talking about very generally how much of a spread there is in your data. Okay, these two I would consider to be strong correlations because the points are, they're relatively close to what would be the kind of trend of this data. So looking at this first one, I would say as x gets bigger, y gets bigger, so that's a positive correlation. Okay. On this one, as x gets bigger, y gets smaller, so that's a negative correlation. And then it is important to talk about the fact that 1 or 2 points isn't really enough to change your correlation. It's actually really hard to add points to either one of these and make them the other type of correlation, make them, turn this from a positive correlation to a negative correlation would be pretty difficult to do. Even 1 point, say right here, even though that's a ways away from what the overall trend of what's going on here is, in statistics, we consider this to be an outlier. And for kind of, again, lack of a better idea of it, it's because it lies outside of the normal look of the data. All right, and then what we're going to talk about mainly today, to go along with what we have been talking about, and we've been talking about writing equations of lines and writing them in different forms. Today, what we're going to look at is what we call best fitting lines. And we're going to do this in a pretty generic setting. There are a lot of different, very technical, statistical ways to come up with this best fitting line, or what we might call a trend line. And we're just going to look, pretty basic as far as how we're going to find that line. Okay, we're just trying to, and this one was already given to us, but we could find best fitting lines on these two as well, and we're just trying to kind of split the difference of all the points and find something that somewhat goes, gives a good look at what the data is doing, and sort of fit a line as best we can to that information. All right, so a best fitting line is a line, obviously, that represents the trend of the data. Okay, and more importantly than it being a line, it's what can we do once we have a line? Okay, once we have a line, we can write the equation. So the important thing here is that we can find an equation that can be used as, trying to think of the other word. Yeah, having a hard time with it. I don't want to say used as, but I'm going to change it a little bit. Used to tell what happens between two data points and then I'm also going to say or to, I'm going to put it in parentheses or quotations, sort of predict the future. And this is where it's mainly used, the idea of trend lines. So, maybe there's a point in here like at -1. I don't actually, well, I do have one. I can figure out what should happen at -1 once I have that equation, right? I can figure out what should happen, and sort of judge that against maybe what I have, or if I just had a hole in my data somewhere in the middle that I wanted to know, where I wanted to know what should happen here, I can figure that out. And that's the between two data points. The other one would be predicting the future, kind of, or the past. I can figure out, well, what should happen at -10 or even -8. You know, where should this data point be at -8? Or even in the positive sense at +8, where should the data point be? So that's sort of the power of trend lines, is not only can we just put a line on the graph, but once we have a line, we can find its equation and use that equation. So here we're going to look at an example that's going to help us approximate a line of best fit. It says here that the table shows the forearm lengths and foot lengths without shoes of 18 students in Mr. Gall's classes. After graphing the points, draw the line that corresponds closely to the data and write the equation of the line. Okay. And this is what we're going to end with. So I did the graphing part for you. We don't have to worry about that. But the way we're going to use this, and the way, again, the very informal way of doing this, it's not the best way, but it is something that works, is to pick 2 points. And this can kind of be a process of guess and check. I'm going to make a red line through this data. And I've already even picked those 2 points for us. I picked 2626 and 1920. In order to do this really well, I do want to pick 2 points that are quite a ways apart on my graph to sort of help me make this decision of what the equation is, and just to see how well it fits the data. Okay. So using those 2 points, again, I've picked those 2 points, and I'm just going to draw the line between them and extend that line out. And I can kind of see that pretty close. It looks like the y-intercept may be pretty close to 18. And if I sort of judge the slope a little bit, it looks like it goes, based on my scale, it looks like it goes up 1 and pretty close to over 1. But we do want to sort of justify those things. Okay, so I want to find my slope and I want to find my y-intercept. So once I've picked my 2 points, it's really a process that we've done already, and it's find the equation of a line that goes through 2 given points. And so we're going to use those 2 points there. If we didn't like those 2 and we wanted to come up with something that was maybe a little bit better, we could adjust one of the points that we picked and see if that did any better. And so what I mean by that is that I could compare that, and what I'm comparing really in a lot of statistical models is I'm trying to minimize the distance between a given point and the line that I have, right? So I'm trying to minimize all of these, and maybe it's the perpendicular distance that I'm typically concerned with. Like, how far away are these, and how can I minimize that as best as possible? Okay, how can I minimize all these little distances between the points? And again, that's kind of the formal way to look at it, and we are looking relatively informal through this process. So let's go ahead and pick those 2 points and see what we can come up with. So I've got 2626 and 1920. Those are the points that I'm working with. 1920 and 2626. Oops. So I'm going to start off by finding my slope with y2 minus y1 over x2 minus x1. And so y2, we'll call that 26 minus 20 over 26 minus 19. 26 minus 20 is 6. 26 minus 19 is 7. So it looks like my slope is going to be 6/7. It wasn't exactly 1, but it was pretty close to 1. Okay. And you'll find that more often than not when you're working with statistics that your numbers aren't going to be very nice. They're just, by nature of the beast, they're not going to be the nicest values. So I've got my slope, and so I'm going to put that into my slope-intercept form. And we'll say plus b. Now the key here is that even though I have all these points on this graph, I do need to pick one of the two that I'm building the line from. So let's say that we go ahead and pick our first one as our x and our y. And so we're going to say, oops, 20, 20, 20, 20. 20 equals 6/7 times 19 plus b. And what might be helpful at this point is a calculator. That opened up way over there. Okay. And so I'm going to look at, the way I'm going to do 6/7 times 19 is I'm going to go 6 times 19 and then divide by 7. And it may actually be easier to deal with decimals because this one's going to give me a pretty nasty decimal anyways. Okay. So I'm actually going to turn 6/7 into a decimal as well. That's going to be 0.857. So really what I did is I turned this into 0.857 times 19 plus b. And I should have dealt with that. Should have wrote down that first. And we have 16.2857. Let's call it 286. So 20 equals 16.286. And to solve for b, I do want to subtract 16.286 from both sides. And so we have 20 minus 16.286, and we get 3.714. And so that equals my b. Getting that information from this, it's kind of looking like my scale was off just a little bit, but that's okay. We're going to go with the math that we got from everything. So I'm going to write it all as decimals. I don't really like using decimals because I know that I rounded at something, or I rounded at some point. So y equals my slope. I'm going to keep that as my decimal. 0.857 x plus 3.714. Okay. One thing that's really nice to use when you're dealing with statistics is spreadsheet programs. They can help make this information run a little bit smoother and sort of get you kind of a quicker answer, and also you can typically use their different programs to or their different formulas to come up with different types of how that line was made. Okay, but that's it for today. Make sure you summarize your notes. Get a good score on the mastery challenge, And let's talk about the practice problems that I want to see you do. Let's go with 1 through 5 on practice, and we'll go with all of number 1, which is really the entire application. So let's say we're going to practice numbers 1 through 5, and really all the application, but numbers wise it's just number 1. All right, make sure you let me know if you have any questions on those, and we will see you in class.